were the two main scientific discoveries, and that is, number one, we're able to make atomically precise structures, and that's really the subject of today's talk, how we do that to advantage. The other one that, particularly true in biology, is even at the nanoscale with precise structures, function is heterogeneous. And that's a different talk, and I'm happy to, discuss that with you. Two other key features were that we could use the biotechnology revolution, in particular the development of tools to address important problems, to advantage in terms of inspiration and how to proceed. And then I think the most surprising of all of the things that we found was that, unlike other fields, and we don't understand why other fields haven't done this, but they have not, because of the way nanoscience developed by people from physics, chemistry, materials, engineering, medicine, toxicology, other fields coming together, we learned communication skills in sharing problems, sharing approaches, and developing new approaches that other fields have not. And so it's incumbent upon us to translate that skill into other areas. And I'll particularly, alert the students and postdocs in the audience that you have these skills and your colleagues in other fields do not. So for instance, that's why the BRAIN initiative in the US came from the nanoscience community. That's why we were asked to lead the microbiome initiative by the White House, when that was put together, because we were inclusive in bringing in people from other fields. And we talked about that in these pieces in ACS Nano, and in particular for how to inspire engineering through medicine. In this editorial we wrote with another editor, Ali Kadam-Husseini, and an interventional radiologist, Rami Aklu. So I'll refer you to those, but now go a little further into where we are. Once upon a time, when I was at IBM Almaden, I was first one to move atoms around. I didn't do that to, for graffiti or to make these interesting electronic structures, but rather just to find out what was underneath the atoms out in the middle of the terrace. And that made us realize that this microscope wasn't only a structural tool for measurement, but it allowed us to manipulate, and it gave us this idea of precise structures. I'll add that we also learn very quickly about the spectroscopic capabilities. So for instance, in this famous quantum corral, there's no extra atom right in the middle. That's just an electronic structural feature from interference that turns out it has important chemical consequences. And we'll talk about that as we go along. So to me, the most important STM image ever recorded, was actually a pair recorded together of the same area, was by Joe Strosio and Randy Feenstra. And they looked at the stoichiometric gallium arsenide 110 surface, in which the charge is transferred from the gallium to the more electronegative arsenic, so that all the filled states sit on the arsenic and all the empty states sit on the gallium. And we realized from these data and others that followed that we could put on goggles, essentially, with the scanning tunneling microscope when we did these spectroscopic measurements and look at the molecular orbitals, which are the basis of chemistry. Okay? They're also the basis of the transport. And so, for instance, here's a graphene nanoribbon in which we map the molecular orbitals. We'll get to that. And seeing these nodes shows us that this would make a very bad contact. More on that later. Okay. In transitional metal calcogenides, Taki Lee at Seoul National University did the following functionalization experiment. He filled in vacancies in molybdenum disulfide with alkane thiols so as to passivate the material and improve the electronic properties. So we would suggest taking this a step further and making these molecular contacts, these molecular connectors, into contacts. And we learn to optimize the transport and the charge distribution through the contacts. And I'll show you how we're trying to do that. And emphasis on the trying to do that rather than having already done that. So one way that we came into this world was as follows. We had developed a spectroscopic imaging tool in the microwave frequency range to image and record spectra on insulator surfaces. And we're trying to look at as broad a spectrum of materials as possible. And Dave Valera, who's my colleague both at Bell Laboratories and at Penn State, along with Ralph Nuzzo, a colleague at Bell Labs who moved to University of Illinois, had developed these alkane thiol on gold sulfosum monolayer systems with which most of you are familiar, I'm guessing, where the sulfur is covalently attached to the gold, the molecules tilt over to form these one molecule thick, two-dimensional layers formed from solution, vapor, or contact. Excuse me. And at the time, it was thought the molecules went down randomly and irreversibly and were immobile once they were on the surface. But even before we got molecular resolution, our very first images of these layers showed that all those three ideas were wrong, that the molecules were dynamic on the surface, that they phase separated, that over time they reduced the interface length because that was unfavorable, the cross interactions for these two different terminal functional groups. And as we improved the microscopes and so forth, we were able to get molecular resolution. And we learned ultimately to control the defects in these films so as to be able to isolate individual molecules, pairs, lines, and clusters to study with a STM probe tip in place over this, kind of more interesting penguin. Okay, and so where we took that was we went to molecules that had been discovered to be conductance switches in groups of 10,000 stuck in pores in silicon nitride membranes by the late Mark Reed. And actually, Taki Lee was a postdoc in the group at that time. And we were asked the question, could single molecules switch, with which using those isolation tricks we were able to show. And then we asked the question how they switched, and we worked out the mechanism that it was a change in hybridization when the molecules tilted over, which we could control with electric field. And what that taught us was that the contacts, the change in hybridization of that buried contact was everything. So just like in semiconductors or the other materials we're discussing, the contacts are the relevant functional part. And that led us to develop other new tools, such as the ability to measure the buried interface and the tilt of the molecules, in which we, for instance, simultaneously measured the exposed surface and the bottom bond. And by associating the top with the bottom, we get the absolute polar and azimuthal tilt. That was an experiment that took us about 20 years to make work, but now it gives us the absolute structure and more. We're able to look at buried interfaces, for instance, where there's charge redistribution. We're also interested, let's get that one. We're also interested in the contact conductance. And so we use a polarizability measurement where the contribution to the molecular polarizability includes the electrons from the substrate if the contact is sufficiently conductive. So we could look at the same molecular switches, individual molecules, in the on versus the off state and show that the polarizability changed by a factor of 2. And that gave us a measurement of what the conductance of the contact was. And so even in the non-trivial cases, we have a way to measure buried contacts using these tools we developed along the way. Well, we had been thinking about contacts for longer than that. And in the early days of nanoscience, one thought about if you wanted to connect to a material, what would the best molecular alligator clip be? And as a field, we were under the false impression that if I chose a particular material for an electrode, I should be able to tell you the atom or molecular functional group that would give you the optimum contact. And along the way, what we did is the very first measurements of the conductance of individual molecules, in which we use these saturated alkane thiol chains in combinations of different lengths, measured with STM in the identical structures. So for instance, it was known that here where there are 2 more CH2 groups in this one versus that one, that the physical height difference is 2 angstroms. And in our STM measurements under these particular conditions, we get a 1 angstrom height difference. There was a concern that there might be cooperative effects, so we controlled the assembly such that we had domains of the longer chain, domains of the shorter chain, and then isolated molecules of the shorter and the longer and the longer in the shorter domains. And it turned out there were not cooperative effects. Then by combining many, many such measurements, we were able to map what's the conductance of the molecules. And by extending all the way down to 0 chain length, we were able to get the contact conductance. So that brought up the question, as I said, it was thought that some atoms, would make a better contact than others. And so for gold, there was an argument over whether the sulfur or selenium, which are in the same column of the periodic table, would be a better contact. And some groups said that the selenium would be 5 times more conductive, and other groups said the sulfur would be 5 times more conductive. And there were measurements, there were predictions, theoretical predictions, everywhere in between. And so we went and we set out to put the molecules in the same structure. Selenium's lower in the periodic table. You can tell I teach first-year undergraduate chemistry. So that the selenium's a little bit larger. It actually turns out it's a little more promiscuous on the surface, but we can force it in the same structure. And this schematic is drawn correctly in that the tip had to go closer to the selenolate molecules of the same backbone chain length. And our STM tip height, remember, is a proxy for the conductance. So if the tip has to go closer, that means these molecules are less conductive. And then again, we did many different combinations. And we extended down to 0 chain length and showed that indeed for these backbones, the thiol is 5 times more conductive than the selenol connection. And then we went back into the literature and we said, well, why did all those other groups get it wrong? And we realized that each group had calculated a different backbone. And so that it wasn't that selenium was 5 times worse than sulfur. It was just for the particular band alignment one got from that saturated, straight, and alkyl chain. That was the result. And so the bad news was that if you give me a contact material, I can't just tell you what to use. But the good news is we can tune that band alignment and optimize it by choosing a backbone or functionalizing that backbone to shift the bands on one side or another. Okay, now let's take a little graphene interlude and connect to those prior 2 talks. This is the work of Patrick Hahn, who was a assistant professor in a lab that we had in Tohoku in Sendai, but he was also the student who'd done the tilt measurement in the alkane thiols, and he also had worked on what's called the Ullmann coupling reaction, in which one can bring together aromatic groups on surfaces in a reaction that's been known for over 100 years in organic chemistry and proceeds with 100% selectivity, both in vacuum and in solution. Okay, so Patrick's particular interest was to explore chiral graphene nanoribbons, thinking that the armchair and zigzag edges had already been explored quite a bit. So the armchair, you might remember, as one goes from the semi-infinite planes to narrower segments, that goes from 0 band gap to increasing band gap with narrower chains. The zigzag nanoribbons have interesting spin properties along the edges that different groups have been exploring. And as I said, we knew a lot about this Ullmann coupling reaction, and so that Patrick was able to design a precursor that would give him on the surface an intermediate that could then by reaction be zipped together to give these chiral graphene nanoribbons. And this is very much along the lines of Klaus Mühlen, who's spoken at previous AAFM meetings. He's really the star of this field. Okay, and the reason we use copper surface in this case is that it interacts strongly with aromatics. So if you look at the gold 111 surface, the close packed surface, aromatics sit far off the surface. We've actually measured the interactions of benzene on gold 111 and shown that under the right tunneling conditions, we can peer right through the benzene and show that the reconstruction of the gold 111 is not lifted with the aromatics on it. A silver surface, aromatics sit a little closer, but the copper strongly interacts with these reactants, intermediates, and products. and is able to satisfy the carbon. It ends up being carbon copper bond once we clip off the halogen. And so by designing the halogen precursor and how those will interact on the surface, including through the substrate electrons, we can design what our final product would be. And so Patrick did that. He started showing that we could form these complexes of the reactants. He could raise the temperature to break the carbon-bromine bond and measure the intermediates by lowering the temperature again. And then at higher temperature, he could form the chiral graphene nanoribbon, very much like the arrow pushing that we teach in organic chemistry classes. And so sure enough, in the different growth directions, we got different chirality. And so we've just color-coded these nanoribbons according to what their direction and chirality is, and we alternate back and forth, left, right, left, right, left, right. Nacho Pascal, a former postdoc in the group, now working at Nanogune in San Sebastian, took the next step, which was to take a vicinal surface in which all the terraces are in the same direction. And in that case, by using those narrow terraces, he only got a single chirality of the graphene nanoribbons everywhere on the surface. So I thought that was really beautiful data that we're now following up with measuring spin properties of these nanoribbons. Now, as I mentioned, we're able to do the spectroscopic imaging of these. We can vary the energy of the electrons that are either probing filled orbitals or empty orbitals, depending upon which way the bias voltage is placed. If we make our tip positive with respect to the substrate, then we measure the filled orbitals coming out of the graphene nanoribbon. We can do things like slide a bromine atom up to the edge of the graphene nanoribbon and break what's essentially a particle in a box into particles in two boxes by manipulating the molecular orbitals in that way. And and along the lines of what Rod had said about referees, and this was really a comment on our paper, came in saying that under different conditions than we had used, that one got a different reaction product, and therefore our mechanism must be wrong. And we took that comment very seriously and reproduced the experimental conditions that the authors of the comment had written, and discovered that indeed we do get different products, but we had high resolution microscopes and showed that our mechanism was still correct. But what got me particularly excited about this and really jumped us several years ahead in our thinking, we had this idea of contacts already, but we had no idea how to pursue it. And so this gave us the idea that, look, all these joints are contacts. Let's go explore their molecular orbitals. So when we look at a straight segment, right, we see a smooth wave function, continuous wave function, no nodes. Some of you who know me know that I have PTSD about phase in orbitals and tunneling. That's a much longer story. And if we were all at UCLA, we might go out to a bar in the evening and discuss it over drinks. We'll have to save that for another time. If we just look at what in the conventional STM image, the topography, this junction looks like it may be a good contact. But in fact, if we look at the phase by measuring the differential conductance, we show there's a node, and that's a bad contact. And so if we go over here to these, all these stripes, that's the kind of thing that gives me nightmares. And that's not what we'd want for contacts. So it's hard to imagine making devices that are just straight, although I will say the Berkeley group has come up with a very clever way that one might do that. But what we then want to do is make a combinatorial set of precursors that then form structures on the surface, measure all the different contacts that we get, develop a predictive theory to say, okay, here's how you get the best contacts, and then we can design the precursors that'll snap those together. And we've done some work along those lines already. I'll point out that Klaus Mullen and Roman Fezel jumped into that controversy with a non-contact AFM, measured the structures, and showed that indeed, our mechanism had been correct. In a lab in Beida at Peking University, Ling Bo Jing started to functionalize the edges of graphene nanoribbons as a way to vary the molecular orbitals and also to get them to assemble, and showed that essentially the band gap only depends upon the length, whether you put the in this case, sulfur atoms on the same side of the graphene nanoribbon or alternating or anything in between. And yeah, that just shows the variation of the band gap. And we can use the electronic properties of the surface to choose which ones we get. And I think there's a lot to follow on there. Other groups have also done this side group functionalization, including my colleagues here at UCLA, including our next speaker, Rick Kainer, working with theorist Anastasia Alexandrova, Ken Hauk, and then experimentalists Sarah Tolbert, who's in the office next to me, and Eve Rubin, as well as some of our editors at ACS Nano, including Andrew Wee and another one of our lecture laureates and EAB members, Qianping Lo. So what they've been able to do is put nitrogen on the edges and then use that for assembly as well as manipulation of electronic properties. And the Berkeley group has done this, these clever surface syntheses in which they vary the width of the armchair graphene nanoribbons in which to build, quote unquote inline device, or to use side group functionalization in the zigzag graphene nanoribbons in another way to manipulate the band alignment and thereby build an inline device. So there's a lot of creativity that can go into these structures. None of us had pulled them off the metal surfaces and worked with them yet, but I think there are opportunities to explore here to work out how we optimize these contacts. Let me move over to molecular system and tell you something about how we can use control of charge in molecules in contacts and band alignment. So instead of those linear chains that I showed you earlier that have flexibility and thus have what are called gauche defects, kinks, that are dynamic in the system, that they have tilt boundaries on the surface that lead to another kind of defects, we realized that if we used upright, symmetric, rigid molecules, that by symmetry, we can remove most of the defects that are found in those self-sum monolayers. So our favorite family of cage molecules that do that at the moment are the Carburine Diols. So these are boron cages with 2 carbon atoms. And unlike what we teach in high school chemistry, the carbon here is behaving like boron. So each carbon atom has 6 bonds instead of what we normally think of as the maximum of 4. And that's because it's behaving like boron. I haven't shown all the hydrogens on here, but each atom has a hydrogen. And so since carbon has 6 bonds, it's electron deficient. And wherever the carbon atoms are on the cage, that's where the positive dipole points. So here, since the carbons are effectively on the side, we end up with a neutral surface and dipoles in the plane of the surface. Here, since the carbon atoms are on the exposed end of the monolayer, we end up with a positively charged surface. And one of the neat things about these cage molecules is that their structures are determined, their lattices are determined by the projection of the cage on the surface. So all of this family form identical structures. And you can see it's even difficult to identify where the domain boundaries here are, because the only kind of boundary one gets in a complete monolayer is an offset and registry that's either translational or rotational. And there are actually 5 domains here, and we've developed mathematics to determine those automatically. Okay, and we can show on the nanoscale or the macro scale the charge on these surfaces. And a postdoc in my laboratory, Jay Kim, figured out that he could use this for band alignment for organic electronics, where the idea is in the active layer, you want to match the contact, which in our case here, we've measured both gold and silver. And people like Seth Martyr at Georgia Tech use a polymer interlayer that they fluorinate in order to add negative charge in order to shift the bands. But that has the property of making the interlayer more like Teflon. And so one changes the wetting properties. And so what Jay showed was with a monolayer that's mixed between these 2 layers, we could tune the band alignment by 1 EV, and each one of these points is 40 devices. We don't change the wetting properties of the polymer we don't change its morphology, and we're off to the races. And so the same ideas apply, for instance, when we make contacts to the transitional metal calcogenides. We can choose the carburane that gives us the charge where we want it in order to get band alignment to the material. And the functionalization of these has been completely explored. And we have it turns out during the Cold War, there were big groups in both the United States and the Soviet Union exploring the chemistry of these and scaling the syntheses up to the ton scale. And so the chemistry of these is fully mapped. We know how to make them in large quantities. These two are commercially available. We have access to many, many others. And we work very closely with the heirs to both the American and the Soviet groups. So let me just finish up with some ideas on spin, where we have these same ideas of using chiral materials to get spin selectivity. The chirality-induced spin selectivity was discovered by Ron Nauman at the Weizmann Institute, with whom we've been collaborating in looking at photoelectrons coming through DNA layers. Recently, we hired Clarissa Ayo in electrical engineering, who's looking at the role of chirality and spin in biological processes in what's called quantum biology. And one of our hopes is to be able to take spintronics up to or close to room temperature by this kind of control. There's a paper that we hope will appear in ACS Nano shortly. We just have a minor revision, but it's already available on arXiv if you want to see some of these ideas. And so the nice part about tunneling is we're measuring at the energy scale at which we would be worrying about transmission. There have been a lot of arguments over time about quantifying or even the existence of this effect. And to me, the nail that sealed the deal was this experiment that Ron Nauman and Bert Mayer from Eindhoven published in JAX, in which when one does water splitting, a side product is peroxide, but that depends upon the electrons coming in with opposite spins. If one only had parallel spins, then one could turn off the hydrogen peroxide production, which they were able to do in the experiments described in that experiment. And so everything after that has really been looking at, okay, how do we optimize this effect, and how do we improve the spin selectivity? And we've done measurements on pattern DNA on surfaces where we build in the controls, where we have do basically 100,000 measurements on the same system at the same time in fluorescence or photoelectron measurements. We use the spin polarized low energy electron microscope at the Molecular Foundry. In all of these, we've been collaborating with the UCSD Magnet Center and Eric Fullerton and his team, and more recently, peptides on surfaces where we can, again, change the chirality of the system and show what the energy offsets are and the resulting spin selectivity. And now what we're trying to do with our collaborator Tomas Baza at the Czech Academy of Sciences, who's the heir to that Soviet group and one of the real virtuosos of carburine synthesis, is he has developed a method of producing chiral carboranes. And so again, by patterning on the same surface and being able to flip the magnetic field in Eric Fullerton substrates, we believe we'll be able to quantify and optimize through synthetic design the spin selectivity of systems in just these 1 nanometer thick layers. So I tried to put everyone on every slide as I went along, including our collaborators here. We actually have a visitor from Yossi's group who's going to be speaking later in the conference, Nirsu Kenik. So I'd encourage you to look for his talk. I think, as I mentioned, there's no punchline, but it's an exciting area and a lot to do for people from many different fields. Here's my group and the people who paid for this work, particularly NSF, DOE, Fulbright, Kavli, and Keck. So collaborators around the world. And, it's there's really an opportunity here for us in many different fields to design, to measure, and ultimately to figure out how to construct the the contacts to control the chemical, physical, electronic, and spin properties. Those you know me know I love the movie Groundhog Day. So after the somewhere between 3,000 and 30,000 days put in by our grad students and postdocs, we hope to be able to make these beautiful interfaces. And I'll stop there and try and leave a little time for questions.
Thank you very much, Paul, for this inspirational talk. And we indeed have a couple of minutes for questions. So if there are any questions, please feel free to raise your hand and ask a question, unmute yourself, or we can unmute you, or post the question in the chat, and I will read the question to Professor Paul Weiss. Any questions?
Everyone's going to grab a quick coffee before Rick's time.
Well, again, I think people have been maybe confused because there are no questions, no time. And the recording has been stopped. Now? Well, again, if there are no questions at the moment here, I'm not sure whether you want to address the issue.
Yeah, and Yuri, I'll see you on Sunday in Atlanta.
Yes, I hope we want to see you on Saturday night if you're coming earlier.
I come in very, very late. Yeah, well, I'll see you.
Well, then till Sunday here. And it's about time to start our last presentation in this session, which will be delivered by Professor Rick Kenner, who is a conference co-chair. He is also distinguished professor of chemistry and material science and engineering at UCLA, and also Dr. Myung-Ki Hong Endowed Chair in Material Innovation here. Rick, you have 40 minutes for your presentation.
Great, thank you. And I also want to thank Professor Imran Shakir and his team for organizing this conference under very difficult circumstances. And I hope to see you all in person at our next meeting at UCLA. With that, we've heard some really interesting talks this morning, and I'd like to continue and talk about our work on the synthesis and energy storage applications of graphene. And I don't need to remind you about the different carbon allotropes, but I'll mention briefly different ways to make graphene. We've heard some really nice ways to make graphene. I'm going to show you how to make really defective graphene because that's what's needed for energy storage. So graphene, of course, is a single layer of carbon. It's a building block for zero-dimensional fullerenes, one-dimensional carbon nanotubes, and two-dimensional graphite. My favorite, well, we'll go through a little bit about some of our early work on how to make graphene. We all know about Novosov and Geim's work with Scotch tape to make samples of graphene, but also you can think about Walter de Heer's group doing the reduction of silicon carbide to make graphene. Rod Ruoff, we heard from earlier, he pioneered the chemical vapor deposition of graphene on copper. Johnny Coleman's group looked at liquid exfoliation, which is another way to make graphene. And Dan Lee's group looked at solvent-assisted stacking. Of course, there are hundreds of other contributions, really important ones to this, but I just picked out a few. This is my favorite picture of pyrolytic graphite. And this is what Novosov and Geim used with Scotch tape. And this is from work from Neil Bartlett's group back quite a while ago. But this is a piece of pyrolytic graphite the size of your thumb. And what we're doing is hitting it with a laser. And of course, a normal material heat up in 3 dimensions, but graphite is not a normal material. And so it only heats up in 2 dimensions. And that's basically because all the phonon modes, all the chemical bonds, the sp2 bonds are all along the plane and they conduct heat. as well as the conduction electrons due to the overlap of the pz orbitals. They all conduct in this plane. And so if you hit the laser here and you touch over on this side, you'll burn yourself, but if you touch the top, it's cold. And of course, a single layer is graphene, and graphene would show the same sort of property, except that this is a three-dimensional form of graphite. Now, back in the year 2000, 4 years before Novosov and Geim did their work, I had a knock on my door at UCLA, and Professor Tom Hahn introduced himself from mechanical engineering, and he asked me if I could produce a single layer of carbon. And he said, everybody is using carbon nanotubes to reinforce polymers, but it's unlikely to work because the problem with carbon nanotubes is they're one-dimensional materials. And in order to reinforce a polymer, you need a two-dimensional material. And he showed me mechanical calculations to prove this. And then he asked me, when I told him I probably could make him a single layer carbon, he asked me how that's possible. And I said, well, it's been known for over 100 years that graphite's a layered compound and you can do intercalation chemistry. And so I said, I just hit it with potassium, and you can heat graphite with potassium at 200 degrees under inert atmosphere, and you'll make a material, a first stage intercalation compound known as KC8, it's bright gold compound. And I said, I just take this material and exfoliate it. And he said, oh, that's a great idea, you got to do that. So we did, and we hit it with alcohol, and the potassium goes to potassium hydroxide, the layers exfoliate, and when we sonicated, the layers scroll. And here's a Lacey carbon TM grid, and you can see the carbon nano scroll, and it's so thin you can see the Lacey carbon right through it. Here's a more tightly wound scroll, here's a whole lot of scrolls. So our goal was to produce graphene, and in fact, we did that in subsequent things. These are our few layer, and in the year 2002, we filed the first patent on how to make graphene 2 years before it was discovered. And then in 2003, we published this paper in Science on this chemical route to carbon nanoscrolls. Now, what's interesting is what Novosov and Geim did is they put it on Scotch tape. And this is a very important point because graphene by itself is not stable. If graphene finds other carbon, it simply restacks and graphitizes. If it finds itself, it will form these scrolls. And so this is a way to make graphene, but it's probably not the best way to make graphene. And so after Novosov and Geim published their work, we realized that if graphene's ever going to be useful for large-scale applications, and we're particularly interested in energy storage, it's going to have to be made by chemistry. And so I switched my line of research, a lot of other people did too, to look at graphene oxide. And graphene oxide, of course, is a very old material. It's over 150 years old. Here's a paper by Brody back in 1860. And what's been known about graphene oxide is if you take graphite and you oxidize it, and something like nitric acid and potassium permanganate as an oxidizing agent is quite good, what you do is you put carboxylic acid groups and hydroxyl groups and epoxide groups, and then it disperses in water. And what we've learned in the past dozen years is disperses in water as individual sheets. Now, of course, these are not conductive, they're insulating sheets, but if you could deoxygenate them, you can get back to graphene. And so this is a way to produce massive amounts of graphene. It's not the perfect graphene that we've heard of in earlier talks today, but it is a way to get large quantities of it. And so what I'm going to show you is we can take this graphene, and once we have it dispersed in water, we can make graphene paper. I don't have time to tell you about electronic devices, but we heard about some beautiful electronic devices earlier from Professor Ferrari. And we can make chemical sensors. I won't have time to talk about that, but we'll look at graphite oxide foam, we'll look at light scribe lithography, and we'll look at energy storage using supercapacitors. So first, a little bit more about taking graphene oxide and chemically deoxygenating it. So one of the first experiments we did is we simply put it in hydrazine, the graphene oxide, to bring it back to a form of graphene. And it disperses in water, and it shows the Tyndall effect. The Tyndall effect is if you hit a laser through it, if it were a solution, the laser would go right on through, but in fact, it scatters light, and you can see the red laser here. And the reason it does this is because you have individual sheets of carbon with a negative charge. And so they all stay apart from each other and they stay dispersed in the water. And we know that because it shows the salt effect. So if you take any salt, and sodium chloride will work, it simply neutralizes the charge and they all flocculate out. And if you take these pieces and you look at them under atomic force microscope, you can see you have very large pieces of chemically produced graphene. And here's an AFM probe, and you can see about a 1 nanometer step height. And this is one way of looking at graphene. Of course, we heard earlier that a better way is to look at Raman spectroscopy, and there's many other ways. But at the time, these were some of the largest pieces produced. And this method is quite useful, easily scalable. We published this in Nature Nanotechnology, and this paper has been cited over 9,000 times. So it's a very popular paper on how to convert graphite to graphene oxide and then back to a form of graphene. And once you have that, we've got large quantities of graphene. We can just take a beaker full and run it through filter paper, and we can trap carbon, and we can make chemically converted graphene films. And so we just peel it off the filter paper. And so this is graphene piled up, literally tens of thousands of layers. Now you may ask, well, isn't that just graphite? Well, graphite's actually three-dimensionally ordered. It's AB stacked, but this material is just randomly stacked, but it's quite strong, and you can see it's highly reflective. Now, one of the things you can do with graphene oxide is you can freeze dry it, and then you get this material that looks like this golden brown material. And one of the early experiments we did is we just lit it on fire, and I'll show you that here. It looks like it's burning, but in fact, you'll see that most of what's left is this black carbon. And so what it's really doing is deoxygenating. It is burning, but what's going off is CO2. And you can do this with graphene oxide paper and a flash of light. So here's a camera flash. We bring up the graphene oxide paper, hit it with a flash of light. And you see it absorbs the light, it gets hot, and again, it blows off CO2. So two completely uncontrolled reactions. But it's possible to control these. And one way to do that is using a light scribe device. It's a $25 device that you can put in your computer stack. And it's comprised of a 780 nanometer laser and a very sophisticated computer program that will raster any image. Plus, with the laser, it has a magnifying glass. And so if you look at this current potential curve, graphene oxide, or graphite oxide if you like, is an insulator. But once you hit it with a laser and convert it to graphene, it becomes a good conductor. And you can raster any image you like. So this is graphene oxide on plastic. You can see the golden brown color. You hit it with the laser, and you can draw little circuits. And so basically what we're doing is we're creating graphene, the black conductor, on graphite oxide, the golden brown insulator. And you can use this to make devices. And in fact, you can actually raster any image you like. So we paid an artist for a person with a computer for their brain, and we produce this in laser scribe graphene. So the part that's very dark is graphene. The part that's very light is graphite oxide. And the gray part in between is simply partially converted between graphite oxide and graphene. And of course, this was published in ACS Nano, Paul Weiss's journal. Great place for publishing nano things. All right, now, one of the things we looked at is we were interested in the electrochemistry of this material. And what's interesting is if you look at the peak separation, and this is a current potential curve, so this is a cyclophotomegram, the peak separation approaches the theoretical limit. It's 0.0595 volts. And here's the Nernst equation down here, and the theoretical limit is 0.05916. So this is a real experiment. It's not quite at the limit, but it's about as close as you can get. And from this, you can calculate the speed of moving charge. And in laser scribe graphene, we can move charge at 10 to the minus 2 centimeters per second. If you look at graphite, it's 10 to the minus 4 centimeters per second. So what's interesting is once you make this laser scribe graphene, it's 100 times faster than graphite. And so that suggests that a good use would be energy storage, because as we know, essentially all lithium-ion batteries use graphite as one of the electrodes, and many other batteries use graphite. It's a standard electrode material. Yet now we have material that's 100 times faster. So we're particularly interested in energy storage. I don't need to tell you that if you're interested in green energy, the wind doesn't blow all the time, the sun doesn't shine all the time, so we need to store it. And often when you need your electronic devices, they're not charged. So one could make something that charges much faster using graphene. Now here's energy and power. So if we think about this, power is how fast you can deliver something, energy is how much you can store. So in a sense, a capacitor is a high-powered device, but doesn't store much energy. Conversely, a battery stores a fair amount of energy, but it's fairly low power. And so what we're interested in is making a supercapacitor, hopefully combining the high power of a capacitor with the high energy of a battery. And I took this from Maxwell Technologies' website. They're a company in San Diego, but they're the leading producer of supercapacitors. And supercapacitors are already $1 billion business. They're used for backup power for cities. They're used to turn windmills. And one of the reasons they're used to turn windmills is because a battery can't respond fast enough, but a supercapacitor can. And in many ports these days, when you lift a container off a ship, when you put it back onto a truck, the lifting takes a lot of energy, but when you put it back, if you have a supercapacitor, you can get over 40% of the energy back. And so this is a good way to cut down on energy usage. There's also a fleet of buses now running in China 24/7, and they're powered completely by carbon-based supercapacitors. So Maxwell makes supercapacitors by taking coconut shells and roasting them, and you get a form of carbon that can be used. And so these buses run continuously, and every 1 to 2 miles, there'll be a charging station. As people get on and off the bus, within a minute or two, you can charge up these buses. This is one of my favorite uses of a supercapacitor. This is in Europe at a train station. There is a revolving door connected to a supercapacitor, and it runs the lights in the restaurant next door. So this is human-powered energy. Here's a Ragone plot, which is power density in watts per kilogram versus energy density in watt hours per kilogram. And what one wants to do is achieve both high power and high energy. And this is the goal for the US Department of Transportation for electric vehicles. And what's interesting is graphene by itself, in theory, with a capacitance of 550 farads per gram, could solve this problem. So here's graphene on this chart. Now, the problem is when you actually go and try to make a device out of graphene, you don't get 550 farads per gram. You only get about 100 to 150 farads per gram. And of course, the problem is restacking. So a single sheet of graphene has a surface area of 2,630 meters squared per gram. But that means that you can access both sides of each sheet. And so if you put 2 layers together, you lose the bottom half of the top sheet and the top half of the bottom sheet, and the surface area per gram drops from 2,600 to 1,300. If you had 3 layers, it would drop by 1/3, or 4 layers by 1/4. And so if you look at this, if you get 100 or 150 farads per gram, it simply means that on average, you have 4 layers of graphene. And so when you build a real device and try to scale this up, you get much less than the theory. And so we've done a bit better, and I'll show you why. And it really has to do with the form of graphene that we're making. It's defective enough that it prevents it from restacking. And that is the whole key. So how do we make our devices? Well, the simplest way is we can take a DVD disc, put a piece of plastic on it, put graphene oxide on, this golden brown material. We can tell our laser to darken the whole thing. And then we can simply peel this off of the disc, and we can put it together and we can make a device. And of course, these devices look like batteries. There's 2 electrodes, a separator and an electrolyte, but they work by a very different mechanism. And that is the electrolyte's going to be near every surface. And simply the negative electrode will take positive ions, the positive electrode, negative ions. And you can, because everything is surface, you can do this very quickly. And so that's how a supercapacitor works. And our original devices were very flexible. It's easy to make flexible devices. Now, this is an interesting experiment. We told our laser to draw stripes on our disk. And so where it's converted, this is laser scribe graphene, and where it's not is just graphite oxide. And if we look under a microscope, you get a good idea of what this material looks like. So graphite oxide is this beautiful layered material. You can see it here. When we hit it with the laser, it absorbs light, it gets hot, and it blows off CO2. And what's left is a fractal. How do we know that? Well, because we can look at several different attributes. And this is a graphene, but it's the world's most effective form of graphene. Now, why do I say it's graphene? Well, graphene has 3 attributes. It has high conductivity, which we can measure. This has high conductivity. It has high surface area, in theory, 2,630 meters squared per gram, where our material has somewhere between 1,500 and 2,000 meters squared per gram. So it's not quite single layer material, but it can't be because it's ordered in the third dimension. In other words, it's connected, or maybe I should say it's disordered in the third dimension. But this is exactly what you want. And the reason we know it's a fractal is because you can measure that high surface area. You can get down to that level. And the other thing is that graphene is pure carbon. Well, even if we do this experiment in air, we've gotten to above 99% carbon. So basically, by burning off CO2, it leaves behind this porous network. If you add an electrolyte, it will fill in these pores and you can access every surface, or just about every surface. And so this is why this works so well for electrochemical devices. So here's the activated carbon that's used in commercial supercapacitors. Here's our material on plastic that we can make little devices out of. And if we look at a cyclovoltammogram current and potential, of course, graphite oxide doesn't store any charge, it's an insulator. But as soon as we hit it with a laser and make it conductive, you get this beautiful rectangular wave, a textbook of capacitance, and we've made a supercapacitor. And so we can compare our material, the stack capacitance versus current density, and you can see this versus a commercial material. So in blue is the commercial material and red is our material. And at low current, they both look pretty much the same. But as you run them harder, the commercial material will eventually fall off and our material will still keep performing. And so we can run this above 4,000 milliamps per cubic centimeter. Now we can look at how fast these materials are by looking at the phase angle as a function of frequency. And we can compare these to an aluminum electrolytic capacitor, to an activated carbon supercapacitor than our own material. And what you'll see is that the activated carbon supercapacitors have a time constant of about 10,000 milliseconds. When we go to our laser scribe graphene, we're over 300 times faster. So our material works quite fast. It's not quite as fast as an aluminum electrolytic capacitor, which is on the order of 1 millisecond. However, this stores very little charge. It's interesting that if we could speed up this number and get down to the level of aluminum electrolytic capacitor, you could think about using this for things like line filtering. I'll show you that this is becoming a possibility. So the way we can speed this up is we've been looking at the effect of carbon nanodots and how they interact with graphene. In a carbon nanodot, there's many ways to make them, but one of the simplest is you can take citric acid and urea and you can hit it in a microwave and you'll get a carbon nanodot. And here you'll see a whole lot of dots that we've gotten. They're all less than 10 nanometers of graphitic domains. And in fact, they're centered around about 1 nanometer, but there is some distribution, as you can see from this. But it's possible, depending on what you start with, to put a lot of different functional groups in. So you can put in oxygen, you can have epoxy groups, you can have OH, hydroxy, you can have nitrogen with pyridine groups. And so there's a rich chemistry of this. And Volker Strauss, who spent a couple years in my lab as a postdoctoral fellow, and he's now at the Max Planck Institute, brought us some of these ideas on carbon nanodots. And what we've done is we've looked at what happens if you put carbon nanodots into our synthesis from graphene oxide using a laser. And so we just simply add some carbon nanodots dispersed in water into graphite oxide. We hit it with a laser. And what's interesting is when we look under a microscope, we can actually find, here's the graphene, and here's where the carbon nanodots actually go in. And they seem to repair some of the defects in the graphene. And you can look at the Raman spectrum and you can show that things can improve up to about 25% mass fraction. But probably the most interesting thing is you can reduce the time constant. And we've gotten the time constant down to less than 1 millisecond, down to about 0.3 milliseconds. And so now you can think of these things as possible doing line filtering and other things where you need very fast electronic responses. All right, getting back to our supercapacitors, these are completely flexible devices. How do we know? Well, if we run a current potential curve as a function of bending angle, you can see that as we bend this, and you can see the picture here of bending, that all the cyclovoltammograms fall on top of each other. So it really doesn't matter. My students made a little movie.
Started.
And what we have here is a supercapacitor that we charge for a few seconds. It runs an LED. You can see the LED is lit. We're bending this supercapacitor, and it has no effect on the LED. So you have a flexible electronic storage device. And for good measure, my students took a piece of graphite oxide that was reduced. So this is chemically reduced graphite oxide, and they put it in line as a conductor. So we just wanted to demonstrate that you can use this chemically reduced form of graphene or laser reduced form of graphene as both a conductor and an energy storage device. And then you may ask, well, how would I run a computer or any other electronic device? And if you look at the back of your computer, it runs at about 14.4 volts and 4,400 milliamp hours. Now, our aqueous devices run about 1 volt. Our non-aqueous about 3, and ionic liquids we can get 4 or slightly more. But I just took 4 aqueous devices. So here's potential versus time. So a 1 volt device, we put 4 of them in series, we get out 4 volts. If we put 2 in series and 2 in parallel, we double the voltage from 1 to 2 volts, we double the area under the curve. So simply by stacking these devices together in series and parallel, you can get out any voltage you want. You can get out any current with enough of these things. So this is a good way to build devices. They have very good cycling life. Here's 10,000 cycles. You can see they have very high capacitance retention. Here's their shelf life. They look pretty good. This is about 4 months. And so they're quite stable. So then you may say, okay, well, what do we need to do? Well, what we need to do, if we actually look at this Ragone plot, power density versus energy density, here are commercial supercapacitors. So they're considerably better than that. Here's our aqueous devices, our solid state devices, organic and ionic liquid. But if you compare them, they're comparable, let's say, to lead acid batteries as far as energy storage, but they're nowhere near lithium ion batteries. So if you really want to use these for energy storage, what you really need is either to combine them with batteries, which is one approach, but probably a better approach is to make hybrid devices that start to approach lithium ion materials. And the question is, how do we do that? And one of the neat ways of doing that is looking at electric double layer capacitors. And so what we want is materials that have more energy storage than carbon. And a good one is manganese dioxide. Manganese dioxide is a material that's used in alkaline batteries. So if you go to the store and you buy, my favorite store is a dollar store, so you can get about 10 of these for $1. And what they are they're filled with manganese dioxide and a lot of carbon. They often have 30 to 40% carbon because manganese dioxide is an insulator. So they need carbon black just to conduct. And so what my point is that manganese dioxide is an incredibly cheap material. There's less than a penny worth of it in an alkaline battery. And so one could think of combining that with graphene and making a device that stores more energy, because this is a redox active material. And it has over 1,000 farads per gram. And so what we wanted to know is, could we make a pseudocapacitor, what's really called a hybrid capacitor, by combining manganese dioxide with graphene? And this works quite well. There's many ways to do this. You can do this chemically or electrochemically. And we're basically using our laser scribed graphene as a structure to hold the battery type material. And so we can grow different amounts of manganese dioxide inside this, and we can look at what the results are. So here's what it looks like under a microscope. So you can see the layered structure of the chemically reduced or chemically converted graphene oxide with a laser. And these things that sort of look like cauliflower-like structures, that is the manganese dioxide. And we can look by XPS and we can see that it's in the right oxidation state for the electrochemically active form of manganese dioxide. And then we can look in using EDS, and we can see that the carbon spread throughout and the manganese and the oxygen. So basically we have a very nice distribution of manganese dioxide throughout this carbon lattice. All right, we can build our devices, and here they are. And when we look at this, here's the current potential curve. We get, again, these very nice rectangular waves. We're getting pure capacitance out of this material. And what's interesting is we have high stack capacitance, but I want to focus on the bottom right-hand side here. And when we look at this, the theoretical capacitance of manganese dioxide is 1,370 farads per gram. And so if we use a lot of graphene on the order of 90% and around 10% manganese dioxide, you can see we can get out about 1,200 farads per gram. So we start approaching this theoretical limit. Now, keep in mind that manganese dioxide is an insulator. So by itself, you couldn't get anything out of this. And so we're using graphene as a scaffold to extract all the energy out of manganese dioxide. So that's quite good from a theoretical level. On a practical level, you really want to go the other way. You want to use very little graphene and a lot of manganese dioxide, just because manganese dioxide is so cheap. And if we do that, if we go to about 5%, if we go to about 5% graphene and 95% manganese dioxide, you can see we can extract on the order of 500 farads per gram. And so this stuff works quite well. And what this says is that the way you should use graphene for energy storage is graphene should just be the scaffold, and you can stuff all sorts of battery materials into it. And so we're excited about that possibility. And when you look at this and compare this to commercial devices on a mass basis all in, what you find is that this manganese dioxide hybrid capacitor is much better than anything out there. It has a huge amount more energy storage capability than lithium ion capacitors or commercial supercapacitors. Now, some of our very recent work is to put in things like vanadium dioxide, because you can actually store more energy using this. And so what we've been using here is a combination of vanadium chloride and graphite oxide. And so we can just coat this on graphite paper. We can hit it with a laser. And so we can make this complex that is really a composite between vanadium oxide and graphene after hitting it with a laser. And you can scale this quite massively. You can see this very large piece, and here you can make some round structures, and you can see what it looks like under a microscope. And if you're more interested, a paper on this just came out this past month in Advanced Energy Materials describing this in much more detail. Now, I also want to talk about making tiny devices, because I think one of the things that graphene is good for, because you can make flexible devices and you can make really small devices. And so in this case, what we're interested in is taking designs that are in the literature, and then ultimately what you want miniature devices for is pacemakers use little tiny batteries. There's radio frequency devices, there's MEMS sensors, and there's hearing aids. And so you can get little tiny lithium ion batteries, but I'll show you that you can do better with graphene and supercapacitors. And so here's some designs for interdigitated electrodes, and you'll see our host, Yuri Gagazzi, did some early work on making some of these designs. And so we simply borrowed some of his designs, and we can produce this with laser scribe graphene. So again, we take a piece of plastic, we coat it with graphene oxide, and in this case, we tell our laser computer program to go and make over 100 micro supercapacitors. And these supercapacitors have this interdigitated design. And so we're just simply going to have two electrodes, one positive, one negative. It makes no difference which we want. We can switch them around. And you can see the laser converted graphene. It's dark, it's conductive. You can see the graphite oxide. We're using that as the insulator. We can just put a drop of electrolyte, and this will work quite well. And when you do this, what we find is the more interdigitated electrodes, the closer together, the higher the performance. And so here's 4 interdigitated electrodes. This is 8, this is 16, and of course the 16 works better. We just put a drop of polyvinyl alcohol with sulfuric acid on this. If you look at the stack capacitance, you'll see that the 16 sandwich structure has a very high stack capacitance, much higher than the other ones. It has nice charge-discharge characteristics. There's a little bit of an IR drop you can see here, because there's a little bit of resistance in the system, but not a whole lot. And you can see the stack capacitance is quite high, and it's certainly better than any commercial supercapacitor. And you can run this at 20,000 milliamps per cubic centimeter, and it still performs quite well. You can then put this on a Ragone plot. And so what we're doing here is we're plotting power density in watts per cubic centimeter versus energy in watt hours per cubic centimeter. And here's a aluminum electrolytic capacitor. It has very high power. And here's our laser scribe graphene. And if we use an ionic liquid, we can get power certainly equivalent to an aluminum electrolytic capacitor. So these are very high power devices. What's interesting is we can get energy densities comparable to lithium thin film batteries. So for these little tiny devices, we can get both high power and high energy. And that says something. It also may say that lithium thin film batteries don't scale down very well, but these do. And so you can now start thinking about this. If you wanted to power, let's say, a little tiny device, maybe you have a Band-Aid where you want to distribute medication, or you have something that you want to put on the skin, you could think about a flexible electronic device that you literally print, and you can make energy storage devices. All right, so basically, I hope that I've showed you that laser scribing enables you to make fine-tuned patterns of graphene. You can make high-performance supercapacitors. You can combine with metal oxides, and we just looked at a few, but in the literature we published on half a dozen different metal oxides to make these hybrid capacitors. And you can mass produce these with a DVD burner. And if you want more information, please look at some of our papers on graphene for battery supercapacitors and beyond, design mechanisms of asymmetric supercapacitors. And we have one that just came out in small called Graphene's Role in Emerging Trends of Capacitive Energy Storage. Now, I want to give you a better idea of what we're actually doing. And so I'm going to show you a movie made for Nova, the public broadcasting thing. It's called The Search for the Super Battery. And I think this will describe what I've been trying to explain a lot better than I could.
There's a lot of talk about renewable energy, but how feasible is it? A major barrier, believe it or not, is battery storage. And that's where something called supercapacitors come in. They run on static electricity, and they're capable of recharging and delivering power faster than batteries. But they don't store as much energy yet. Enter chemist Rick Kaner. You see, supercapacitors are limited by the surface area available for holding electrons. And Kaner's developed a technique to produce electrodes with lots of surface area out of graphite.
This is what graphite looks like as it comes out of the ground. It's a mineral.
And this is what's in a pencil.
Absolutely. So a pencil is nothing more than graphite combined with clay. So this is the material that's used in essentially all batteries as at least one of the electrodes. So the question is whether you could make this in a high surface area form. And that is where graphene comes in.
Graphene is the strongest material ever tested. It's a layer of carbon that's 1 atom thick, giving it extremely high surface area. Kaner says 1 gram of the stuff would cover 4 football fields.
Graphene provides the high surface area and conductivity necessary to store large amounts of charge.
Which means graphene might just allow supercapacitors to be even more super. And Kaner's lab has come up with a surprising way to make it. It starts with plain old graphite. This is a chunk of graphite oxide that was mixed with water and then freeze-dried. Maher El-Kadi hits it with an ordinary camera flash.
Big flash.
Yes, big. So just watch what's going on.
Okay. Oh,
The pulse of light's converted to heat, burning away the oxygen and leaving behind graphene.
that's graphene right there.
So what's left over, we call it now graphene foam.
Kaner's lab has developed a system to print exact designs. A layer of plastic gets coated onto the surface of the CD with a solution of graphite oxide. Once dry, it's inserted into a CD laser labeler.
Oh, that's wild.
But instead of doing its usual job of etching a label, wherever the laser hits the dried graphite oxide, that spot's transformed into graphene.
Oh, I like this technology.
Aside from a graphene likeness of David Pogue, El-Kadi's printed 2 graphene electrodes.
Obviously, there's a huge worldwide market for CDs with pictures of me in graphene, but I'm guessing that these are more important to the future of mankind. You etch circuits out of the graphene?
Yeah, so these circuits are basically micro supercapacitors. And this stores as much charge as these like very bulky capacitors that you will find in any electronic device.
You mean this totally flat pattern right now could hold as much charge as this capacitor?
Yes, and we actually made them store 1,000 times more charge as this size of a capacitor.
If we could scale this to the size of electric vehicles, then you could actually, instead of pulling into a gas station, you'd pull into a charging station, and within minutes, your car would be ready to go.
An electric car that you can charge as quickly as it would take to fill up?
I would definitely like to see that happen, and that's exactly what we're doing.
There's a lot.
Okay, with that, I would like to thank my students and collaborators who've done all this work. You just met Dr. Maher El-Kadi, and he's running Nanotech Energy, and they're one of our sponsors. And they just did a press release recently. They've developed a non-flammable electrolyte for lithium-ion batteries and have raised $65 million this year in pursuit of that. I mentioned Dr. Volker Strauss at the Max Planck Institute, many other students, but I want to talk about one of my collaborators, Professor Mir Musave, who did a sabbatical in my lab and is planning to come back this fall for another year. And we've been collaborating on a lot of these experiments, and he has developed some very new battery anodes, and he will talk about this in tomorrow at 9:55. So if you get a chance to hear his talk, I think you'll learn a lot of interesting things. We've also had some nice support from initially from Maxwell Technologies, who I talked about their work on supercapacitors, the National Science Foundation, and others. And with that, I'd like to thank you for your attention, and I'm happy to answer any questions.
Thank you very much, Rick. Questions to Professor Kenner? Please type your question or raise your hand using the reactions button in your Zoom. I don't have access to YouTube, so I won't be able to take any questions if there are questions showing up in YouTube. I don't see any questions in the moment. Maybe we'll give another minute if someone is typing right now. Again, I was delighted, Rick, to see a talk about supercapacitors, my favorite devices. By the way, the Ragone plot used in the middle, coming from our 208 review with Patrice Simon, is a little bit dated. We published an up-to-date, really looking through the latest literature Ragone plot in the updated review of materials for supercapacitors last fall in Nature Materials. It just has more advanced devices here because definitely the field moved forward. So 12 years later, we produced like an updated version of it here.
Yeah,
well,
good.
Since I don't see questions popping up, I think we are ready to close this session. Again, I would like to thank all our keynote speakers in this session for excellent talks, excellent coverage of various aspects of carbon nanomaterials, from synthesis to devices, applications, and characterization. And as I understand, we have a 20-minute break now. And after that, there will be another plenary session with 2 more talks, including my own presentation. See you later. Professor, you will be chairing that session in 20 minutes after a short break.
Hi, Jim. Jim, you're still muted. Do you want to text run your slides? Okay, unmute. Me? Okay.
Oh, okay.
All right.
Yeah, I couldn't unmute it. You have to unmute me, so.
I have a little bit setting.
I was trying to tell you that in a muted state. So